question like this one here, where a 15-kilogram object is released from rest at the top of a 5-meter high slope that is 10 meters long at an angle of 30 degrees and allowed to slide down, and we are asked to calculate the final velocity when this object reaches the bottom of the incline. Would normally have been done by first calculating the amount of work that was done by each force, and then we can use the work energy theorem that says that the net work done on this object is equal to this object's change in kinetic energy. Now, this is also possible to do by realizing that there is only one non-conservative force acting on this object, and that non-conservative force is the force of friction. And as we can see, if we draw a free body diagram for ourselves, we can see that there's a force of gravity acting downward on this object. There would be a normal force acting perpendicular to the surface and a frictional force acting up the incline. And so what we can do here is we can realize that any change in the system's energy is going to be as a result of that non-conservative force. And so we use the formula: the work done by the non-conservative force is equal to the change in mechanical energy of that system. And since there is only one non-conservative force, that being friction, it is going to be the work done by friction is equal to the change in the mechanical energy for the system. In order to calculate this, we first need to find out what that friction force is. We do that by realizing that the force of gravity acting downward on this object can be resolved into two components, those being Fg perpendicular and Fg parallel, where perpendicular refers to perpendicular to the slope and parallel refers to parallel to the slope. And we know that this angle here is the same as the angle of the slope. And so we can calculate our value for Fg perpendicular by seeing that that is the adjacent side of the triangle, therefore Fg cos of theta, where Fg is 15 kilograms times 9.8, 147 times cos of that angle 30, and that tells us that the perpendicular component of gravity is then 127.31 newtons. Now, using that, we can calculate the friction force by saying the friction force is equal to the coefficient of friction times the normal force, where the coefficient is given as 0.2. Our normal force, we know, is equal but opposite to the gravitational force, or the perpendicular component of gravity. And so we can say that is also 127.31 newtons. And therefore we know that friction is 25.46 newtons. So now we can calculate the work that is done by this friction force, 25.46, multiplied by this object's displacement. As we can see, the displacement is down the slope, and the displacement is given to us as 10 meters, so 25.46 multiplied by 10, and we know that the displacement and the motion and friction are always in opposite directions to each other, so therefore cos of 180. The object's change in mechanical energy can be written as the object's final mechanical energy, E mech final, minus the object's initial mechanical energy, E mech initial, which can then be rewritten as EP final plus EK final. The mechanical energy at the end is the sum of the object's kinetic and potential energy, and the initial mechanical energy is the initial object's kinetic and potential energy. This can then be used to write down the values that we have here. The final potential is the mass times gravity times the final height. The final kinetic energy, 1/2 mvf squared, minus the initial mass, gravity, and height, minus the initial half mass times initial velocity squared. What this allows us to do then is we can substitute the values that we have. We know that the final height, when the object reaches the end point, the height is 0, and therefore the final potential energy is 0. At that point, the object still has a mass of 15 kilograms, and we are trying to determine what its final velocity is at that point. We know that at the starting point, this object is 5 meters off the ground, where we are talking about vertical height because this is height relative to the gravitational force. So that is a mass of 15 kilograms, 9.8, and the initial height of 5 meters, minus the initial kinetic energy. We were told that this object starts from rest, and therefore the initial kinetic energy is 0. What we have now is we have an equation with one unknown, and that allows us to solve to find that the final velocity of this object is equal to 8.003, or just 8 meters per second down the incline. So as we can see, we can use the fact that there's only one non-conservative force acting on this object to calculate an unknown. And the added benefit here is that this does not only refer to kinetic energy, but refers to the total mechanical energy. There are scenarios where it will be easier to use our work energy theorem. We could have used that to solve this problem here. Work energy theorem, which says that the network is equal to the change in kinetic energy. The network on this object would have been the work done by the force of gravity plus the work done by friction equal to the object's change in kinetic energy, where the work done by the force of gravity automatically takes into account the components of gravity, and we would still get the same answer, but it is important to be able to solve these questions in multiple ways. It is fairly common that a question like this would not give the vertical height of an object at the top of the slope, where it is important to remember then that when you are given an incline and some angle theta and the length of the incline, we can use trigonometry to solve for the unknown, where we can see that this is the opposite side of the triangle, and therefore we can say that that opposite side, or the vertical height, is equal to our hypotenuse x multiplied by sine of that angle.